Hi guys, so let's look at challenge 7 in your notes. So this is the 2002 exam question. In this question, we're told that a spacecraft has a mass of 50,000 kg and is approaching a space station with a constant speed of 2 meters per second. The spacecraft slows to 0.5 meters per second to lock onto the space station. We're asked to calculate the mass of the gas that the spacecraft must expel. Any questions looking at the conservation of momentum start off in the same way. We write down the momentum before equals the momentum after the collision. Okay, and from here I'm going to read the question and draw a diagram of the information given. Okay, so we're told we have a rocket moving at a speed of 2 meters per second before the collision, so before it slows down. And then afterwards, the rocket slows down because gas is expelled, so gas is released, and the rocket moves off at a slower pace. Okay, from here, we need to look at what we need to find and write down those values. So to find your momentum, we need mass and velocity. So we need to find the mass of the rocket before the collision, and the velocity of the rocket before the collision. That's the initial velocity of the rocket. We also need the mass of the gas expelled, which is what we're looking for, and the velocity which the gas is expelled at. We need the mass of the rocket after the collision, which will be the same, and we need the velocity of the rocket after the collision, which will be slower because the rocket is slowing down. Okay, now we've written out what we need to find, let's read the question and fill in for the values that were given. So we know the mass of the rocket is 50,000 kg. I know that the speed of the rocket before the collision is 2 meters per second. I don't know what the mass of the gas is, that's what I'm looking for. I know that the velocity of the gas is 50 meters per second. So the gas is expelled at 50 meters per second. I know the mass of the rocket is unchanged. It tells us that in the question. So the mass of the rocket is still 50,000 kg. And the speed of the rocket after the collision when it slows down is 0.5 meters per second. From here, we have the values that we need, so we write down our equations for the law of conservation of momentum. That is, the mass of the rocket times the initial velocity of the rocket, so m1u1, is equal to the mass of the gas times the velocity of the gas plus the mass of the rocket times the velocity of the rocket. Once we have our equation written out, we just need to substitute in our values for our letters. This gives us 50,000 times 2 equals the mass of the gas, which we don't know, so we'll keep that as m for and g for gas, times 50 plus 50,000 times 0.5. From here, we're going to expand our brackets and solve for our unknown letter m. So 50,000 times 2 gives us 100,000, which is equal to mg times 50 gives us 50 times the mass of the gas, plus 50,000 times 0.5 gives us 25,000. Okay, so we want to solve for m. That means we want m on one side of the equation and everything else on the other. So I'm going to move the 25,000 to the other side of the equation. This gives us 100,000 minus 25,000 is equal to 50 times the mass of the gas. This leaves us with 75,000 is equal to 50 times the mass of the gas. We want the mass of the gas on its own, so we divide both sides by 50. This leaves us with 1,500 kg is equal to m, the mass of the gas, which we were asked to find. Okay, part 2 asks us in what direction should the gas be expelled. So let's think about this. The rocket is slowing down, so that means that the rocket needs to have less momentum than it did before. So that means the momentum, the size of the arrow of the rocket, needs to be smaller. So the gas needs to be expelled towards the space station or forward. So let's look at this in terms of arrows to make sure we're correct. So the momentum of the rocket before the collision is a certain size. After the collision, we want the arrow of the rocket, the momentum of the rocket, to be less. So that means we need another arrow traveling in the same direction, which carries some of that momentum. So the gas is expelled in the same direction as the rocket. This leaves us with the size of the arrow before the collision, the momentum before the collision, is equal to the sum of the arrows after the collision. That's the size of the arrows or the momentum after the collision. In part 3, we're asked to explain how the principle of conservation of momentum is applied to a changing direction in which the spacecraft is traveling. So anytime we're asked to explain the principle of conservation of momentum, you state the principle of conservation of momentum. That is, the momentum before a collision is equal to a momentum after a collision, providing no external forces act. And from here, we relate this law to the movement of a rocket. So when gas is expelled, the rocket moves in the opposite direction. This allows it to change direction. So gas is expelled, rocket moves in opposite direction.